Hey guys, welcome back. Today I have a very interesting question for you. How does Linux run a program? That's what I'll be talking about. Okay, I have a program called Deep Linux. It's just going to print Deep Linux, and this is the source code for deeplinux.c, which is just the printf, right? Now, the question is, the binary for this program, when I run it, what happens? How does Linux run this program? How does it execute this program? Well, most of you probably know that I'm running this inside the shell. So here, if I do ps, it's going to give me the processes that are running inside this shell, which is the bash, and of course the ps command. And this is my bash. And within this bash, I'm running Deep Linux. So on the right side, I'm using Trace Compass, and I have loaded up Trace Compass with an LTTNG trace of the system when I ran Deep Linux. I loaded up in Trace Compass. I've enabled the scheduler events and the system calls to take a look and see what I can understand from what's happening here. Okay, so you can see here I have my bash here, which creates a child called Deep Linux. So bash is actually running my Deep Linux. And of course, bash is run by Terminator, which is this black application like terminal, and then that's run by the GNOME shell, which is the GUI that I'm using here. Okay, but we're interested in the part related to bash and Deep Linux. So just to give you a quick glimpse of what's happening, first off, bash would do a clone. Now, the clone system call, what it does is that it creates a clone of the parent process, meaning bash here, which is an exact replica of bash, and then that would change personality into Deep Linux. That's very interesting, right? So here the clone starts, right? And then here the clone finishes in the parent, right? So if you see syscall exit clone, the return value of clone here is 688780, which is the PID of the new created child, the Deep Linux process, okay? So this way, the parent knows the PID of the child, and it also knows that, okay, after the clone is being executed, now I'm the parent, okay? Because after clone is executed, how would you know if you're the parent or the child? Because now you're two clones. You got to know somehow if I'm the parent, then I have to do my parent business, or if I'm the child, then I have to do my child business, in this case being running Deep Linux, okay? On the child side, the system call returns value of 0, as you can see here. So the value of 0 is returned. Then I know that I'm the child, so I go on and, play my child business, whatever that is. Okay, so that's the first thing. Something also interesting is that you can see here that somewhere towards the end of this clone being run in the bash, the parent, the child process is scheduled on the CPU, indicated by this orange interval, meaning that, okay, a new process is placed on the CPU queue. And as you can see here in the events, there's a scheduler process fork event, right? The parent is bash, right? And that's the PID, which has actually done this, okay? Now, at this point, the child is also a replica of the bash, right? But what this event means is that within the clone system call, the kernel, what it does is it would invoke the scheduler, telling it, hey, Linux scheduler, I have forked or cloned a new process, and I need you to take care of that and place it on run queue. Okay, so you can see here, you get the schedule wake up new. So there's a new process that needs to be woken up, right? And then here, there's a switch happening. Scheduler switches from the idle process to the new process, which is bash. Because yet, at this point, the child is still called bash. It hasn't changed its name, but you can see that it's got the new TID here, right? This new TID. Okay, so that's something interesting to note. That's part of what happens in the clone system call in the parent. Now, after the parent does the clone system call, it does a bunch of things which aren't really that important. But the important thing is that at the end, it would do a wait. Now, this is part of the user space code of bash program, right? So some developer writing the C code for bash had to go in and write this so that bash would wait for the child. So wait is you enter wait here, and then at the end you kind of block, right? Because you're waiting until the child finishes or exits, right? So the pattern here is that the parent clones the child, knows that it's the parent because the PID that it gets as a result of returning from clone is not 0. Then it goes on to wait for the child, right? So it waits for the child. Okay. Now, when the child finishes off its own business, like this is how the child does its thing, right? Towards the end, it's actually making a exit system call, right? This exit is what kind of unblocks the wait system call of the parent. So now the parent can continue whatever it was doing. So the parent has to wait for the child and then continue execution. Now, there are other patterns of multi-process programming as well. The parent doesn't always have to wait for the child, but it's best practice if the parent waits for the child, right? To clean up after it, right? Because bad things can happen if you don't wait for your child. So here, after exit, you see Deep Linux exits. It's all resources for Deep Linux are kind of taken away, and it's taken off the scheduler, whatever, right? And then bash continues to function. Okay. So having said that, let's do a deep down on the child process. So here's the clone, as I said, right? The clone returns. So now I'm a new replica of bash. Now a bunch of system calls happen here, which aren't really that much interesting for me. What I want to point to is this next system call exec, VE, or just exec, right? This system call, as you can see here, is what executes a certain binary on disk. So exec is basically asking the kernel to execute a file, a binary executable file, within the context of this new child. This is where the child changes personality to a new process, to a new program, actually. Not a new process, but a new program. Okay, so you see that the file name is Deep Linux, and then these are the argv and all the environments passed from the parent to the child, right? So what this exec does is that it loads Deep Linux binary. It opens this binary file, which is an ELF file in Linux, and then reads the ELF file, parses the ELF file, loads different sections of the ELF file, including the code, the data, the different shared libraries, and maps it into different places in the virtual memory map of the new process, and then starts execution from the first line of code related to the file Deep Linux. Okay, so this is execve. So this execve is where the new child process changes personality to a new program. Okay, so after the execve, this is no longer a replica of bash, it's Deep Linux. Okay, so that's the first thing. Now, what else happens is that if you look here in the these system calls, you will see that I have the access system call, and then a bunch of open. These open files, right? So we have so many open system calls, right? I wonder what these are opening, right? See, so many open system calls, right? So many open system calls. Let's just see what these are opening. Just gonna zoom in, pick one, okay? This one. Okay, it's trying to open libc.so. Now, what about this one? Again, tries to open libc.so. So it's actually searching for libc.so, right? And let's go here again. This one is trying to open the, this is a binary file, contains the cache for all the paths to all the shared libraries on my system. Kind of like something like that, okay? So what's happening here is that my program is searching for its libraries, the libraries with which to which it depends. If I do LDD Deep Linux, I'm going to get these libraries. Now, forget about this one. This is libc, and this is the loader, which is a dependency for pretty much all executable files. These two actually. So it's got to go and find these because it has to load them in memory, right? Because for this program to run, it needs to load up these shared libraries in its virtual memory space. So it needs to go and find it on disk and load it. Okay, and that's what it's doing. Now here, apparently it found it, right? Because now it's actually going and opening this one, and the return value for this is 3. This system call is returning the value of 3, meaning that yes, it was successful, and 3 is the file descriptor, which can be used as a handle to access this file. So next is read. I'm reading from file descriptor 3, which is this same libc library that I just opened, and I'm reading from it. And then I'm again reading from it. So I'm just continuing to read from it. Then pread is also read. I'm just continuing to read. I'm continuing to read. And then we have a bunch of these reads. And then after that, I'm doing an mmap. Now, if you pay attention to this mmap, you can see that part of the parameters for this mmap, here. Sorry, is a file descriptor in this mmap, which is file descriptor 3. It's just the same file descriptor used when I opened the libc shared library. So what I'm doing here is that I'm reading this shared library to kind of parse and understand the different sections in this shared library. And once I realize all the different sections and decide how I want to load it up in memory, then it's time for me to do the mmaps and map different segments of this file to the virtual memory space of the process, Deep Linux. And that is done via mmap. So after this follows a bunch of mmap system calls, as you can see. All of them would have file descriptor 3, meaning that some way or the other, they're actually mapping parts of this file into the memory space. And so the place that they start to map from within the file is at this offset, right? So you see here that the offset for the first mmap is 0. For the second mmap, the offset is 139.264, and for this one, the offset is something else. So they're actually reading off different offsets corresponding to different segments in the binary and loading them up, mapping them into the virtual memory. These different segments correspond to code, to global data, and whatnot, right? So let's just move forward. Again, a bunch of mmaps, and, well, this one, unknown system call. And the next interesting part would be, okay, here, break. The break system call is where you kind of create the heap. So now I've loaded up my shared libraries, right, libc. Now I need to create the heap. This is the part that the process would create the heap. The return value for break is the address. This is an address. This is the, I think this is where the heap starts. It's got to be where the heap starts. No, sorry. This, well, depending on the parameter that's passed into it, this could be either where the heap starts or ends. I'm not 100% sure, but yeah. Okay. So after the heap is created, so this part is where the heap is kind of extended, if you may, right? Then I get this write system call, which is kind of mysterious. What is this write? Well, actually, it's a write to file descriptor 1. File descriptor 1 in Linux is a special file descriptor, which is always standard output, meaning your screen, your terminal. Okay, file descriptor 0 is standard input, meaning your keyboard. Whatever you write into file descriptor 0 is basically your input. Anything you write to file descriptor 1 would show up on the terminal, and file descriptor 2 is standard error output. So this is where we are actually doing the printf, right? This printf of Deep Linux, right? And then eventually it exits. There's the exit, which kind of unblocks this guy, the parent, and it continues doing its own parent stuff. Okay, so this is what happens at a bird's eye view when you run a program in Linux. Again, kind of recapping, the parent process, in this case the shell, does a clone, creates an exact replica of itself in a different independent virtual memory space, and that will be the child process. The child process returns from clone, both return actually from clone. Parent calls wait and blocks until the child exits. The child would actually then do an exec, which would load up a file, an executable file, and copied over the current child memory space, giving it a new personality, making it into a new program. So now at the end of exec.ve, it will no longer be bash, it would be deep Linux. Then deep Linux would go on to load up, open actually several different paths and try to search for all the shared libraries that it needs to load in its virtual memory space. Once it finds that, it would open each shared library. In this case, we'll have only one, opens it, reads different sections of it, parses the shared library, different sections. Once it realized the different sections, it would mmap them into different parts of the virtual memory space of the new process, deep Linux. And then after that, the actual execution of the program would start. In this case, a simple, oh, actually before that, the heap is created. And then after that, we start executing the program. So actually we're just starting right here. And then at the end, you exit. If I just zoom out, you see that the part of this program of mine, right? This part, this thing here is only from here to here. That's it. All the rest is stuff that you don't see, that it's happening behind the scenes. And there's even more to this. So to show you a little bit more, I'm going to run strace, which traces the system calls as they're happening for my executable. So I'm just going to say strace and then deep Linux, right? These are all the system calls that are made by deep Linux. So these system calls are the API between user space and kernel space. So you can see it starts from exec. You can't see whatever's before this, you can't see really here, right? And that's a mystery, because the reason is most of the stuff that happens before here on the child are done by the Linux loader, and you can't see that here, but I can show you in a different way. Okay, this only shows you from exec, and then this is the part where you actually create the heap, and this is actually, you can see now here in strace you get a better decoding of the system call parameters, actually searching for libc, and then it would go on to actually find libc here, because now it has some return value, positive return value. Here it was all negative, meaning I couldn't find it here. So it's actually going through a long list of places that it guesses libc would be. Eventually it finds libc here and it reads it, right? And you can see that this is the elf header at the beginning of libc, which means that this is an elf file, and then starts reading. And actually, this is where it's parsing it. So it's parsing this. Now it understands the structure of this elf file, different sections, different segments, whatever, how to load it in memory, and it will start mapping it. So this first part, mmap, you can see that it's read only. So this is the read only part, okay, and this other part is read and exec, meaning this is the code, right? And it actually starts from this offset. So the code, the executable of libc starts from this offset. It's telling it to go into that file, start from that offset and load it up and actually map it into this virtual address space. This is the beginning of the virtual address space, I believe. This is again read-only part. This is read and write. So these are the global variables, I believe. And so on and so forth. And eventually it closes libc. Now there aren't any other libraries to open, to load, so that's it. And here, oh, actually, sorry, this is where it creates the heap. Yeah, this is where it creates the heap. And this is the write, which is the printf. Because you see it says write to file descriptor 1, deep Linux. That's the string. And the return value is the number of characters written. And then it does exit, which is the return 0 that I have over there. And that's it. Done. Okay? Okay. So that was cool, right? But let's see what happens before this and within the context of the parent. So I'm just going to focus on that right now. Okay, so what I'm going to do is I'm going to start attaching strace to the parent process, which is bash. So ps, actually, I'm going to run it over here on this other terminal. So this bash that's the PID for this bash. So I'm just going to say sudo strace, and I have to say sudo because I'm attaching to another process. So I need to be sudo to do that, strace, and then -p, and then this, right? So there you go. Okay, so I've attached to this one, and it's running a select, which is basically it's waiting for input or events on file descriptor 0, which is standard input. So if I type anything, you see that this is going to kind of return, right? And then it's going to read the characters that I type, and then at the same time, it's going to write them, right? Read, write, whatever. Okay. Now, what else? Okay, yeah. So because this bash is going to be running this deep Linux, right? If I just strace this way, it's not going to attach to the child. Strace is only going to follow the parent, which is bash. So what I'm going to do is I'm going to say strace -p, and then I'm going to say -ff, follow fork, right? Meaning that if this process, which is bash, forks, meaning if it clones, if it kind of creates another child, follow the parent and the child at the same time. So I can see system call made by both, okay? So I'm just going to run this, and then here I'm just going to run deep Linux. Great, done. So you see, this is the part where, okay, yeah, here. This is the PID of the child, right? Because the PID of the parent is this one, 188 at the end. So this has got to be the child. And you can see here that the child here has exited and the weight of the parent has resumed. And this is already what we saw in that graphical trace compass representation here when you did exit. This is here. This actually is right here. Is this part? Okay, it's that part. Okay, now what I'm going to do is I'm going to go back and look what's happening before this exec, right? I promised you to show you what's happening here, and this is exactly what I'm going to do. So I'm just going to go back up and until I get to the exec. Okay, so here you see the clone, right? This is the clone of the parent, and you can see that it returns the PID of the parent of the child, right? And then strace says, okay, this new process I just attached to it. And these are all the system calls that we saw that the child was running over in trace compass. And okay, so here we get the exec, right? You can see the exec. But before the exec, what happens before the exec? That's what I'm interested to know. Now, before the exec, you can see that there are some system calls sig action. So what sig action does is that, as you can see, the all these different signal handlers are being defaulted or being installed in a certain way for this new running process. Okay, so this is something that the parent does. Well, actually, this is still the parent part of the code because it's still before the exec, right? So this is some stuff that the parent does before actually delegating to the new process. Okay, the parent, but it's in the child. This is the bash as the child, basically. Okay, so some signal handler magic is going on, and that's pretty much it. Okay, but and then here you see that there are these opens of like it's looking for the shared libraries and whatnot, right? But I also promise you that I'm going to show you how the loader plays a role in all of this. Now you don't see the loader anywhere here, and that's because you're not really seeing the stack. So what I'm going to do is I'm going to show you the stack, okay? Which is the user space code that is making the call to these system calls. Okay, so I'm just going to run this. Let's just give it some space here, and there you go. You can see here that here's the stack. Like if this is my system call, then this is the stack calling that system call. Just going to scroll up, up, up. There you go. Where is it? Clone. See, this is the clone system call made by the parent, this bash guy here, and this is the stack for that. So it's basically in the bash program, obviously, in the bash main, reader loop, execute command internal, shell exec ve, make child, and then it runs the libc fork, which makes the system call clone. Okay, this is interesting. So it's the bash that it's doing it. And let's just go down a little bit. Now you can see that this is a new PID, right? This is the new PID. This is the child part, right? So this 313 process is the child, 188 is the parent. So the child, pay attention, the stack for the child is still in the user bin bash executable because it's still having the personality of its parent. It's still running the same program. It's a different process, right? Okay, fine. But it's running the same program as a different process. It's running bash. It's still before the exec. It still has the bash personality until it does the exec. Okay. So, and then we go on and go on, so on and so forth, until we reach. These are all the signal handler installations and whatever configurations and whatever, right? And here, this is the exec. Okay, so this exec is also run by bash. So bash is inside bash code. We have these functions: execute command internal. This is the code, the user space code of the bash. The developers of the bash program have written these functions to do this. Execute command internal, execute shell exec ve, and then exec ve called, which calls the exec ve. So after this, we're expecting to have the new program Deep Linux be run by this child process. Okay, but something interesting happens before we get to that point. And you can see right after exec, the stack of this child changes from bash not to Deep Linux, but to something else. User lib this ld.so. This is the loader library, right? This is the Linux loader. It's a shared library that loads the programs into the virtual memory space and then jumps to the first instruction of the program, which is the main function of the program, okay? So this is where the loader kind of kicks in. So you actually, when you're doing exec, at the end, you delegate to loader to kind of load the different libraries and then pass control back to the actual program that is to be run, which is Deep Linux. Okay, and you can see that these. So let me show you. The search for this libc.so is done by loader code. Because I didn't write the code to do that. You saw my deeplinux.c program, right? I didn't do that. I didn't write the code. vi deeplinux.c. Oops. .c. What? Yeah. What am I doing? Okay. Oh, this is because. Yeah. Sorry. This is because. Yeah. There you go. So this I didn't do anything. I didn't say, search for libc library. I didn't do that. There's no code here that does that. I can promise you that. And bash is not doing it because it's after the exec ve. If it was before the exec ve, then yeah, we could say maybe bash is doing it, right? But then maybe not. But this is after exec ve, so bash is no longer there in the memory of this child process. It's Deep Linux. So what's happening is that the loader is taking over and doing this, and loading up all the shared libraries for us. So if I go forward, scroll down, just see, yeah, there you go. So you see all these M maps, right? All these M maps of the libc library into the virtual memory space. It's all happening using the by the loader. And then here, this is the first part. I kind of switch into Deep Linux, and then I go execute here, start. So this is actually something that's even run before main. So actually, main is called by a hidden function underline start that's compiled by the put by the compiler. C compiler puts a start, but then that start calls main, right? So start calls libc start main, and this is how all C programs get started. Start calls libc start main, and libc start main calls main. And then here we're doing the IO put s, which is the equivalent of of printf here. This printf is actually this guy, right, inside libc, and that's what we're doing. Okay. So this whole heap being created and everything else is actually part of that. Okay, and then at the end we exit. Okay, so a recap is the parent, when you run a command, clones, creates a replica of itself, and that clone would run exec, which would load up a new binary into the memory space of this new program, the new process, right? The target program, in this case, Deep Linux, right? This part is performed by the parent code, right? Although in a different child process, but it's still the parent code. After this, there is no parent code. So from here to the part where you actually run the program, you pass control to the main. This part where you kind of create the virtual memory address space of this process, and actually you have already created it, but you map all the shared library dependencies into that virtual memory space, right? That is all done by the loader, and the loader is invoked after exec ve. So within the context of this child process, right, before passing control to the first line of code inside the main function, the kernel calls loader, which loads up all the shared libraries and then passes control to the main. So that's how things happen. I hope you enjoyed this video and you have sort of a better understanding of what happens when Linux runs a program. See you soon in my next video. Bye-bye.